Chemical reactions and equations. Lecture number 1. Now let's come to the introductory part. We all know that chemical reactions are very necessary for our survival. Now, some of the daily life examples are the formation of curd and yogurt from milk, the digestion of food in our body, and the process of respiration. A technical example of a chemical reaction is during Diwali, during which we lit a magnesium ribbon coming out of the explosive. It burns with a white dazzling light and leaves as a residual powder of magnesium oxide. Now let's discuss some laboratory examples. One of the most popular examples is the reaction of zinc granules with dilute sulfuric acid, which gives rise to hydrogen gas. The setup of this experiment has been given below. Please have a look. Now, let's learn about chemical equations. First of all, what is a chemical equation? A chemical equation is something which is used to represent what actually happens in a chemical reaction. In a simple language, it is nothing but an on-paper representation of how various chemicals react with each other during a chemical reaction. The components of a chemical equation. There are mainly two major components in a chemical equation, namely the reactant and the other component is the product. Now let's define a reactant. Reactant is that substance which undergoes a chemical change during any chemical reaction, and that substance which has been formed when the reactant has undergone a chemical change is known as a product. So basically, a reactant will undergo chemical change to form a product. This is the basic sketch of what actually happens in a chemical equation. Okay? Now let's discuss an example of a chemical equation. The same old example of Diwali. On the right of your screens, there is a list of what actually happens in this reaction. First we lit the magnesium ribbon, then it burns with a dazzling light due to the presence of oxygen in the air and gives us a powder of magnesium oxide. A schematic has been shown below, and what actually we write on paper is the one which is highlighted in the white light. Mg plus O2 gives rise to MgO. This is a chemical equation. Now let's learn how to write a chemical equation. It's actually quite simple. It follows from a basic rule that the number of atoms of each element on either side of the arrow must be the same. If the number of atoms is not same on both the sides, it is called as an unbalanced chemical equation. And if at all the number of atoms are same in both the sides, then it is called as a balanced chemical equation. Now it is the time to learn a bit about a balanced chemical equation. This actually comes from the law of conservation of mass, which states that the total mass of elements present on the product side must be equal to the total mass of the elements present on the reactant side. In other words, it says that the number of elements on either side of the arrow must be the same. Consider the following example. Now I list down the number of elements in a tabular form as shown below. One can clearly see that the number of elements on the LHS and RHS are same for all the atoms. Hence, the given equation is a balanced chemical equation. Now let's learn how to balance. This job is actually done for an unbalanced chemical equation. Okay, consider the following example. Again, I list the number of elements of each atom in a tabular form. I can clearly see that the number of atoms of hydrogen is same, but for oxygen and iron it is not the same. Hence, the given equation is an example of an unbalanced chemical equation. Now, let's learn how to balance this given unbalanced chemical equation. Step number 1. We have to draw a box around each formula, and we have to ensure that we do not make any changes inside this box. Step number 2. List down all the atoms given in the chemical equation in a tabular form. Step number 3. Start balancing by balancing the oxygen atoms first. Observe the table. One can clearly see that we have 4 atoms of hydrogen on the right and 1 atom of hydrogen on the left. So to balance it, I multiply it by 4 on the left. So my equation becomes the following one. Now, coming to step number 4. In this step, I have to balance the atoms of hydrogen in the same procedure. Consider the given table. I have 8 atoms of hydrogen on my right and 2 on my left. So I multiply it by 4. Step number 5. In the similar way, balance the other atoms excluding hydrogen and oxygen. In this case, I have iron left, so I have 3 on right and 1 on my left, so I multiply it by 3. And step number 6. We have to just write down the finally balanced chemical equation. That's it. Which is nothing but 3Fe plus 4H2 gives rise to Fe3O4 plus 4H2. There's actually one more important last step to complete the procedure of balancing the equation, which is nothing but representing the states of the compound. The states list has been given in the tabular form. One must note that the states must be shown in a smaller case alphabets only. So, my previously discussed example will now become the following equation. This one is a finely balanced chemical equation. That's it. Now let's learn about the factors which actually affect a chemical reaction. The main factors that affect a chemical reaction are 1. Temperature, pressure, sunlight, the atmosphere around, and other auxiliary pigments. Given below are 2 equations which represent in them the factors which actually affect them. We have to note that the factors which affect the chemical reaction must be denoted above or below the arrow in the chemical equation. Now, there are some things to remember while writing down a chemical equation. In case of diatomic atoms, they have to be shown as a standalone molecule. The sign of an arrow represents the direction of action of the equation. A small delta above the arrow shows that heat has been involved in the reaction. One must ensure that we never change the formula while writing down the equation. Balancing is just a numerical method. And one must know that this physical states are always in smaller case alphabets, and all the physical states have to be represented after each and every compound in a bracket. The continuation of the present lecture can be found in the upcoming lecture. Thank you for watching.